In the last episode on retrieval augmented generation, we learned that it is a technique where we retrieve relevant context from internal data sources and then augment it with user's query. We send this combined input to large language models for generating an output. We also learned about vector databases that allow us to store and index unstructured data as vector embeddings. We learned about various methods for comparing two vectors for similarity, such as cosine similarity, dot product, and Euclidean distance. In this episode, we will continue our discussion on vector databases and retrieval augmented generation. Vector databases support different algorithms for searching embeddings that are similar to the query embedding. At a high level, these algorithms can be divided into two categories: exact nearest neighbor or ENN and approximate nearest neighbor or ANN. When using exact nearest neighbor, system compares the query vector with every vector in the database and returns the true closest vectors to the query. But this comes at a high computational cost, especially as the dataset grows. In contrast, approximate nearest neighbor sacrifices a small amount of accuracy in exchange for significant gains in speed and scalability. There are two popular approximate nearest neighbor algorithms: hierarchical navigable small world, which is abbreviated as HNSW, and inverted file index, which is abbreviated as IVF. HNSW organizes vectors into a multi-layer graph structure with different densities of vectors at each layer. You can compare this to a navigation system with highways, main roads, and local streets. The top layer contains very few vectors. You can think of it like a high level map of the cities. Each node or vector acts as a gateway to a broader region of similar vectors. The search starts at this layer because it is fastest to traverse. The middle layers have medium density of vectors. These layers contain vectors from the top layers as well as some more. Think of them as city level roads where the search is refined step by step, narrowing down to more relevant candidates. The bottom layer contains all vectors, including all from the upper layers. It represents a street level detail where the final and most precise search happens. The search begins at an entry point in the top sparse layer. From there, it traverses the neighboring nodes to find a vector that is closest to the query embedding. Once a locally closest node is found, the search drops down to the next layer, using this new node as the new entry point. The process repeats through the middle layers, each time refining the search space. Finally, at the bottom layer, the search performs a more detailed lookup to retrieve k nearest neighbors to the query vector. The result is considered approximate because the algorithm never compares against every vector in the dataset. Instead, it efficiently narrows the search to regions near the entry path and finds the best matches within this constrained space. Inverted file index takes a clustering based approach to vector search. It builds an index by grouping vectors into clusters and assigning each cluster a centroid vector that represents the cluster. At query time, the system first finds k nearest centroids to the query embedding. And then, instead of searching the entire dataset, it only searches within these selected clusters. This dramatically reduces the search space and improves efficiency. IVF is highly memory efficient and scales very well to large datasets. However, when compared to HNSW, it can have slightly lower accuracy, especially if clustering and search parameters are not well tuned. In summary, approximate nearest neighbor search offers a balance of speed and accuracy at scale, and hence, in most real world applications, ANN algorithms are preferred because they can return highly relevant results in milliseconds, even over millions or billions of vectors. So, how can you pick between HNSW and IVF? HNSW excels in speed and precision. You should prefer HNSW when high quality results are critical and you can afford high memory usage. HNSW performs particularly well in CPU bound environments. Therefore, it can be a good choice of algorithm when self hosting a vector database in a CPU server. IVF is better suited for large scale memory efficient search. You should prefer IVF when working with very large datasets ranging from hundreds of millions to billions of vectors and when operating under strict memory or cost constraints. IVF is especially effective in GPU accelerated environments or when you have to create a high throughput system where you need to optimize for queries per second. Both algorithms have tunable parameters to balance accuracy with speed and memory. In HNSW, the key tunable parameters are M, which controls how many connections each node can have in the graph. EF construction and EF search controls the size of candidate list during graph building and search respectively. Higher values of these parameters improve recall, but they also increase memory consumption and latency. For IVF, the main parameters are nlist and nprobe. Nlist sets how many clusters the dataset is partitioned into, and nprobe controls how many of these clusters are searched for each query. A higher value for these parameters leads to higher accuracy but at the cost of higher latency. In order to achieve optimal performance and accuracy from your vector search algorithm, you need to tune the parameters that we just saw. The best way to tune parameters is through benchmarking and iterative experimentation using a data set that closely represents your actual use case. A common strategy is to set a target recall threshold, for example, 90%, 95%, and then adjust parameters until you achieve that level of recall while keeping the query latency within acceptable limits. One practical approach is grid search, where you test a predefined set of parameter combinations instead of trying every possible permutation. This helps narrow down good configurations in a structured and efficient manner. There are also many automated tuning frameworks that can explore the parameter space more intelligently and efficiently than manual search. You can consider any of these automated frameworks. Ultimately, the optimal configuration is the one that balances recall with latency, memory usage, and cost for your specific workload. There is a choice of many purpose built vector databases and also traditional databases that have been enhanced with vector capabilities, such as Postgres or Elasticsearch or Redis and MemoryDB, etc. The purpose built vector databases such as Pinecone, Milvus, Quadrant, etc., have been designed grounds up to store, index, and search high dimensional vectors efficiently at scale. They specialize in similarity search using approximate nearest neighbor indexing techniques and optimized data structures, enabling very fast semantic retrieval over large volumes of unstructured data. In contrast, traditional databases such as Postgres allow you to store and query both structured data and vectors within the same platform. They are useful when you want to add semantic search capabilities on top of your existing structured data without introducing a separate system. pgvector is an extension for Postgres that allows you to store and search vector embeddings directly inside the relational database. These embeddings are stored in a table alongside other traditional fields using a vector data type. pgvector supports different indexing strategies like HNSW or IVF, which speeds up similarity search over large datasets. At query time, the user's input is first converted into an embedding, and then a similarity search is run inside PostgreSQL using operators like cosine distance or dot product to find the closest matching vectors. This makes pgvector useful for a wide range of use cases like semantic search or keyword search, where you combine keyword filters with vector similarity. pgvector lets you treat PostgreSQL as both structured database and vector search engine in one system. And in my experience, it is a very popular choice with enterprises that already use PostgreSQL for storing their structured data. Besides retrieving context from a vector database, you can also retrieve information from your structured data sources, such as your databases or your enterprise or custom APIs using protocols such as SQL, HTTP, REST, etc.